All right, well, what I want to do with you guys today is do some work on combustion and fixing up a approximation we did in our calculations. It'll be the last topic of the year. So what we'll try to do is go over some theory and then do an example problem that would be similar to, say, what's on the homework or what you'll see on test 3. So before we get going, it is Friday, and earlier today I saw a lot of you guys' senior projects. I got to tell you, that was just a lot of fun and a real pleasure to see what you guys produced, and I really enjoyed talking with you all. So congratulations on that. It was just great to see. All right, so combustion. Let me just get going on that. What I'm going to do is draw on this whiteboard a little bit, try to give you a few ideas about what to do. And then I encourage you, when I go through the calculations or pull out some numbers, for you to pause the video and see if you can pull those numbers out yourself. The more you do here, the easier the problems on the homework are going to be, and also the easier the test is going to be. Practice makes perfect. So again, I'll get something up there and say, hey, why don't you pause? Encourage you to do that, and then go to your tables, go to your paper, and work out this and try to get the numbers and compare to what I got. Okay, so let me get going on combustion. Let me just draw something really quickly. And generally, we got a chamber, right? Okay, and we think of there being fuel coming in of some sort, a hydrocarbon in general, okay, and air. And then what's coming out? Well, regardless of what happens, we're going to get some CO2, some H2O, and some nitrogen. And earlier in the semester, when we were working on this, our goal was to figure out, well, how much heat gets released in that reaction? How much heat ends up getting released in that reaction? So that could be represented by some sort of heat coming out. All right? And obviously we want as much heat as possible. If we have a good reaction, we get a lot of heat for a little bit of fuel, and we're on our way towards running a turbine or heating some water or doing something else that's important. Okay, what we did was we figured out the enthalpies of the stuff on the right. We figured out the enthalpies on the stuff on the right, and what we really wanted them to be was as low as possible. And in general, they are. Hopefully, you remember, like carbon dioxide had a very low negative enthalpy. Same with H2O. And the idea then is that energy released in the fuel is almost all of it's coming out with heat, and then hardly any of it is in the carbon dioxide, the hydrogen, and the nitrogen. Okay. Key number for the nitrogen, when we got the enthalpy for the nitrogen, it was always 0 on every single problem that we did. Okay. And that is basically what we need to fix up. We assumed that the temperatures, both at the inlet and the outlet, were a very nice, easy standard temperature. In SI, we did 25, and in English, we did 77 degrees Fahrenheit. So we had 77 degrees Fahrenheit here and 77 degrees Fahrenheit coming out. All right, so how realistic are those numbers? Well, for the air, that's pretty realistic. Okay, the air might be a bit higher than 77, a little bit lower than 77, but somewhere in there. Fuel, that's pretty realistic as well. Okay, somewhere in that range. But these numbers over here are just entirely unrealistic. It is possible that maybe you could have a combustion reaction where stuff goes in the chamber, you get your combustion, and you get a lot of energy out of the carbon dioxide, the water, and the nitrogen, and they come out at a pretty low temperature. Okay, but their 77 is pretty unrealistic. And in general, there are a lot more elevated temperatures, maybe something like 1,000 Rankine. So, as a result, all these things are going to have energy. In particular, the nitrogen is going to have more energy than 0. So how do we go about figuring out what those energies are so that when we do our problem, when we compare the enthalpy of the stuff at the entrance and the total enthalpy of the stuff coming out, okay, of the products, that we have realistic numbers for over here. All right, that's the last topic of the year. It's pretty easy, but it takes a little bit of care. Let's get to work. Give me a second to erase here. While I'm erasing, what I'd like you to do is get table A18E out. Table A18E out. And we'll start with taking a look at nitrogen. Okay, so what if nitrogen was at 1,000 Rankine? What are we going to make its enthalpy? All right, so first thing, what we're going to say for any quantity or anything that's going through a combustion reaction is we're going to say that its enthalpy, H, okay, and a lot of times we're going to do it on a per mole basis, so that's why that bar is up there, is going to be equal to its chemical enthalpy plus its sensible enthalpy. Okay, it's chemical enthalpy plus its sensible enthalpy. Okay, this is discussed in section 15.4, right at the section of 15, beginning of section 15.4. They do a pretty good job of laying it out, and I'm just going to give it a slightly different spin on it, which I hopefully will help you to understand that. Okay, the chemical enthalpy is going to be the same as what we did before, regardless of the temperature. Okay, if I have 77 degree Fahrenheit methane, it's got a certain chemical enthalpy in the bonds. I take that methane and raise it to 90. Is there any change in the bonds? No, same chemical enthalpy. I even raise it to 150 degrees, still the same chemical enthalpy. And the same, that holds for carbon dioxide, that holds for H2O vapor, that holds for nitrogen gas. The chemical enthalpy does not change with temperature. Okay? But the sensible enthalpy obviously does. That's the energy essentially due to temperature, so of course that's going to change. All right, what we've done so far when we come up with these numbers, it's always been with reference to 77 degree Fahrenheit. Okay, so if we were working with some nitrogen gas, give me a second to just get a little picture here. I've got some nitrogen gas, and let's say it's at 1,000 Rankine. Okay, what we would want to do to get its enthalpy at 1,000 Rankine, okay, its enthalpy at 1,000 Rankine, what we would want to do is a combination of its chemical enthalpy, okay, which is the enthalpy of formation per mole, okay, at our standard temperature, okay, enthalpy of formation per mole at our standard temperature, and that's what that O means, okay, plus the sensible enthalpy due to the fact that it's a higher temperature, okay, so plus the sensible enthalpy due to the fact that it's a higher temperature. All right, this we got from tables in the book. That we should know, that we know how to do, and it doesn't change. But how about the sensible enthalpy relative to 77? Okay, I'm going to erase for a second and just work on that. Okay, what we could do is we can go to table A18E, table A18E, and we can find the enthalpy of nitrogen at 77, and then also the enthalpy of nitrogen at 1,000. And work out what those enthalpies are and take the difference. And the enthalpy at 1,000 minus the enthalpy at 77 will essentially give us the enthalpy of nitrogen at 1,000 Rankine. Okay, so I'm going to look up those numbers really quickly. I encourage you guys to pause the video and look them up yourself, and then we're going to try to take those numbers and come up with a value here for the enthalpy of nitrogen gas at 1,000 Rankine. All right, give me a second. Hopefully you guys are looking up those. Enthalpy at 77, I'm looking at table A18E. 77 is not in the table because it's in Rankine. 77 is Fahrenheit is 537 Rankine. So I go to the tables and I'm getting my number. Okay, then I'm going to 1,000 Rankine and finding what the enthalpy is. 6. And there's the numbers right there, okay? At 77, we've got 3729.5, and at 1,000, it's 6977.9. Okay, now these are not the chemical energy. Those are the energies due to temperature. All right, so to work, let's try to finish it off. To figure out what value we're going to use for 1,000 Rankine nitrogen coming out of a combustion chamber, let me write something down and get that up there for you. Its enthalpy, it's going to be its enthalpy of formation, okay, plus how much enthalpy there is due to the fact that it's an elevated temperature, how much enthalpy it has compared to the enthalpy at 77 due to its elevated temperature. So there is our basic equation that we're going to use. All right, so that's easy enough for nitrogen. We're going to go to the tables, and nitrogen's enthalpy of formation is 0, just like we had in the previous, when we previously did these problems. And then the enthalpy due to the temperature is going to be this 6977.9 minus the enthalpy at 3729.5. Okay. Those are in BTUs per pound mole. Those are in BTU per pound mole. Obviously, you can see that you're going to get a positive number. And that what that means then is that nitrogen is going to come out of the combustion chamber with a lot of enthalpy. Previously, when we did these problems, the nitrogen came out with 0 enthalpy. Now it's going to have a lot, and that means we're not going to get as much energy out of our combustion process. All right, good. So that's one example. Right side, when we're doing combustion, we got nitrogen coming out, we've got carbon dioxide coming out, and we have water. Let's just take a look at water at a 1,000 Rankine and see what it looks like. All right, give me a second to erase and we'll get going. So for water, while I'm erasing, for water, what you're going to need to do then is you're going to have to flip through the tables to find the sensible enthalpy of water. A18 was nitrogen. Why don't you go ahead and find the one for water, and we'll get going on that. So what I'm doing right now while you guys are looking is I'm taking a look at some H2O, and by the way, it's going to be H2O vapor or gas, okay, and it's 1,000 Rankine. All right, and I'm writing my basic equation. I'll show it to you guys in just a minute. The enthalpy per mole at 1,000 Rankine of this water is going to be its enthalpy of formation. That's the chemical energy, plus its enthalpy at 1,000 minus its enthalpy at the standard state, which is 77 degrees Fahrenheit. Okay, we're always considering 0 to be at 77. Okay, so that's what we need to do for water. Okay, we need to figure out its enthalpy of formation, and then we need to take the difference between its enthalpy at 1,000 Rankine and then its enthalpy at 77. Which 77 is in Fahrenheit, it really would be 537. Okay, so which one was water? A18E is nitrogen, A19E is oxygen, A20E is carbon dioxide, A21E is carbon monoxide, A22E is hydrogen, and finally A23E is water vapor. Okay, simple enough, simple enough. So I'll start filling in the numbers and we'll see how it turns out. Okay. What's the enthalpy of water vapor at 1,000 Rankine going to be? And this is per pound mole, so I'm going to try to work that out. Well, you can go to the earlier tables that we used towards the end, and the enthalpy of formation of water vapor is negative 104,040, and that reflects the fact that when you have combustion, and you get a bunch of hydrogen and oxygen flying around in that combustion chamber, and they recombine to make H2O, you get a huge release of energy. So we get a very, very negative number for water vapor. And that's what we went at previously. Now, though, it's going to be pretty typical that our water vapor is going to come out at an elevated temperature. Okay, so let's go ahead and correct the numbers. Hopefully you are looking at the tables and finding the 1,000 number and also finding the 537 number. Let me just find those myself and you can check my work. Okay, so there we go. There I got it. The enthalpy of water vapor at 1,000 Rankine. Before we were using a negative 104,040, okay? Now it's going to be higher by this amount because it's above 77 degrees Fahrenheit or above 537 Rankine, and that will be a positive add-on. So once again with water, on the right side of a combustion reaction where we used to have negative 104,040, we won't have as low a number, and therefore we're going to get less energy out of our combustion, which is something we need to take account of if we're going to be realistic. All right, real good. That pretty much sums up the basics of it, and then I think it'd be productive to go through an example. Let me describe the example for you. You might want to write it down really briefly, and then we'll go ahead and get to work. see if we can take our way through the balancing and the computations. All right, so what I'm going to do is I'm going to take ethane, not an uncommon fuel, and I'm going to use stoichiometric air. So what that means is we've got the exact amount of air necessary to take every carbon atom and make it into CO2, every hydrogen atom made into H2O, and we're going to have the products come out at 1,200 Rankine. Not really a super high temperature, actually. In addition, we're going to have them come out at 15 psia, all right? And so to repeat, ethane, stoichiometric air, products at 1,200 Rankine, products at 15 psia. We are going to write a balanced reaction, okay? And then we are going to try to find the heat released during that reaction in BTUs per pound mole. In addition, we're going to compare that to the higher heating value and lower heating value for ethane to try to A, check our numbers, and B, check our understanding, see if we can see what's going on. All right, so I encourage you to go to the tables and find the chemical formula for ethane and get going and start working on your balanced reaction. I'm going to erase and do a little bit of figuring myself, so this video is not going to be super entertaining for a little while, not that it ever was. And we'll compare answers in just a little bit. If you're quicker than me, great. If you're slower than me, go ahead and pause the video so that you can work these things out. Okay. So I'm drawing my reaction. I found the chemical formula for ethane. And I know that I have air coming out. Pardon me. I know that I have H2O coming out, CO2, and nitrogen. All right. Starting to work on my balanced reaction. Okay, so just to start for you guys, that's what the reaction looks like. On the right side, you want to remember that all of those are at 1,200 Rankine. All of those products are at 1,200 Rankine. I probably should have said that the entering reactants are all at 77. Again, is that realistic? Well, air is going to be pretty close to 77. If it's at a bit of an elevated temperature, something like 90, or a lower temperature, something like 40, it'll change the numbers a bit. And ethane could be a little bit higher or lower. That'll change the numbers a bit. For one of the homework problems, the air is at 40, and you can go ahead and do the same type of work. The fuel, we're always just going to do at 77 in this class to make life easy. And if you understand what we're doing here, with a little bit of work, you can understand how to adjust fuel if its temperature is different than the reference temperature of 77 or 25 degrees C. Okay, so now I need to get to work, and I need to solve for X and the coefficients for CO2 and H2O. And maybe you should pause and do that yourself. I'll crank through it. All right, so not a hard one to balance. I've got my ethane on the left, and I've got my air. I got 16.667 kilomoles of air for every kilomole of ethane. Okay, on the right, 2 carbon dioxide, 3 hydrogen, and 13.167 nitrogen. All right, and then pretty soon it's going to be time to get to work and figure out what those enthalpies of all terms within that equation are. But then there's that crucial question about the H2O. Okay, what is the H2O? Is it going to be vapor or is it going to be liquid? All right, think about that for just a second. Is that H2O going to be vapor or going to be liquid? Hopefully you remember we really would like it to be liquid if we're going to have really efficient combustion, because liquid H2O has a lot less energy than vapor. If it comes out as liquid, that means that the energy that was in the H2O vapor initially during combustion is H2O vapor, and if you're really clever about how you set up your combustion, you can get that energy that's in the H2O vapor and have it come out as that's in the H2O vapor and have it come out as liquid. That's called condensing combustion. Very, very efficient. If you ever buy a water heater, look into buying a condensing water heater. You're going to get a lot more efficiency out of it. All right, let's just check ourselves. We could get to work and do the computations, but what do we think? 1,200 Rankine H2O, is that going to be liquid or vapor? Well, hopefully your intuition says it's going to be vapor, and if that's right, if that's your intuition, you're right. What we need to do, though, to be sure, is figure out what pressure that H2O is under, and compare that and figure out what the saturation temperature of H2O is at that pressure. All right, so that's been a little while. I'm going to do that work on the whiteboard, and why don't you guys pause and do that work yourself? What is that H2O coming out going to be? Keep in mind that the products are at 15 psia. So I'm going through the work, and hopefully you guys are going through that yourself. All right, so it's been a little while. Something that you're going to want to have down when you do the homework, and of course you're going to want to have down on test 3. How do we figure out the pressure that this H2O is under? Well, all these products over here are 15 psia, and the pressure of the H2O is proportional to the number of moles H2O, and that's what this equation right here is saying. The number of moles of vapor over the total moles in our mixture is equal to the pressure of the vapor over the total pressure of the mixture, which is 15 psia. By the way, 15 psia, not an unrealistic number for when the stuff comes out of the combustion chamber. All right, so I just cranked through the numbers. The total moles of the mixture is 2 plus 3 plus 13.167, and I got 3 moles of vapor, so I cranked through it, and I got that the pressure of the vapor is about 2.5 psia. So that pressure of the vapor is 2.5 psia. You can go to the saturation tables and figure out what the saturation temperature is, essentially what the boiling temperature of H2O would be 2.5 psia. It's very low, much lower than 1,200 Rankine. It's much lower than 1,200 Rankine. So what we can do is we can conclude that the H2O coming out is vapor. The H2O coming out is vapor. So taking a look at our reaction, we know we have H2O vapor coming out, carbon dioxide coming out, and nitrogen coming out. All of those are at 1,200 Rankine, and then what we have to do is figure out the enthalpy of all those products. All right, so what I'd like you to do while I'm erasing is think about how you're going to go about getting the enthalpy of all 3 of those products, and we'll see how the numbers work. what I'm going to do, you can look in the book. There's a good example in the book. They have their own way of setting up how to figure out those enthalpies. I'm going to do it slightly differently. Okay, you can use the book's way, or you can do my way. Okay, but what I'm basically going to do is set up a table for the products. Okay, the reactants are easy because those are all at 77. Okay, but the products are at 1,200 Rankine, so we've got some work to do. All right, so give me a second while I'm writing this down. All right. Okay. So one way to organize it all would just be to make a table like that for the products. Okay. And for each product, what we want to do is figure out its chemical energy. That would be that number right there. Okay. The enthalpy of formation. By the way, I should have a that line above it. All right. And then we're also going to figure out its energy, its enthalpy at 1,200 and its enthalpy at 537. And we're going to combine those numbers to get its actual enthalpy as it's coming out. All right? You don't need to do it this way, but I found it to be a pretty nice way to summarize things. And then if I have some sort of mistake, I can have a chart to go back to. All right, so I'm going to start filling out those numbers for the three different products, and I encourage you to do the same. And we'll check our work in just a minute. All right, I'm just about done, so if you need to pause, go ahead and do that. We'll take a look at what our numbers are. All right, so going through the numbers. Okay, the first column is what we used every time we did the previous problems. Okay, carbon dioxide has a very negative enthalpy of formation. That reflects the fact that it releases a lot of energy. Same thing with water vapor, a very negative enthalpy of reaction, and we get a lot of energy released. Nitrogen at 77 degrees Fahrenheit had 0. Okay, had 0. All right, so how does it change? First of all, just all I did, and for each of these final numbers are equal, these are all per mole, okay, was I took this value here and then added this and subtracted that, okay? And so I end up making an adjustment for the fact that the product coming out is at a higher temperature at 1,200 Rankine. So hopefully you can see that every single one of these numbers is higher than the numbers that we used to use, okay? And that means that the products are coming out with more energy and less energy is going to be released in the combustion. Products coming out with more energy, less energy released in the combustion. Personally, I think that this is a number to pay attention to here as far as understanding what's going on. What about nitrogen during combustion? It comes in with the air, except if you're doing something like acetylene or some sort of other fuel that's burned with pure oxygen. So the nitrogen comes with the air and it just passes through. okay? It's going to come in with 0 energy because we're going to have it come in at 77 on the problem that we just did. But it comes out with higher energy, 4,690 BTUs per pound mole, okay? And in addition, there is a lot of nitrogen because air is mostly nitrogen. So this is going to result in a lot of energy coming out in the products and therefore less energy released in our combustion reaction. All right, so now we've got just about everything we need to do to finish this off. What we just need to do is go back to our balanced reaction and just take a look at what, and use these numbers over here in order to get a complete equation with all the enthalpies and determine how much enthalpy is released during the combustion. All right, I'm going to get to work. I suggest you do yourself, and let's see if we can summarize how the numbers look. All right, so if you need to pause, go ahead. Otherwise, let's get going. So top line's the reaction. We've got ethane, and then we're mixing it with stoichiometric air. And on the right side, we're getting out our CO2. We're getting our H2O, which is vapor. I probably should have put H2O as vapor, or G, giving us the gas. And we got our nitrogen going out. Okay, taking a look at the energy. That is the enthalpy of formation of ethane at 77 degrees Fahrenheit, enthalpy of formation. Not a super negative number. We're going to drop to much more negative numbers on the right and therefore have energy released. All right? Okay, on the right side, the first number is for 2 pound-mole of carbon dioxide. The second number is for 3 pound-mole of H2O vapor. And the third number is for 13.17 pound-mole of nitrogen. So that's a significant amount of energy or enthalpy that's going out with the nitrogen. It doesn't go to combustion. How do we get the actual energy released? Add up all of these, compare it to that. This number will be a much more negative number than that. The difference is what's released. I'm going to get to work and get those numbers, and you do the same, and we'll compare. Okay, so that's what I got. I hope it checks. Maybe taking a look at the right side, it looks we've got like about 300,000 and about 300,000, so that's about 600,000. And we're coming in at 36,000, so it looks like it would be, a bit over 500,000, quite a bit over 500,000 released, but there's that 61,000 for the nitrogen, and that brings us down closer to 500,000. So I've got 523,984 BTUs per pound mole. All right, that sounds pretty good. What we would like to do is get it per pound mass, because that's going to be more realistic if we actually do combustion. How much energy is released per pound mass? So that just involves taking a look at finding the molar mass of ethane and cranking the numbers. So I'll go ahead and do that. You guys do that yourself. Okay, so there we go. I looked up the molar mass of ethane, and then I did the computation, and I got 17425.5 BTUs per pound mass. Okay, so heating your home, that would probably do about a little over an hour for heating your home, so you'd need to burn about a pound of ethane in order to provide the heat necessary to keep your house warm on a really cold night. All right, last thing. All right, what we did a balanced reaction. We decided whether the H2O was vapor or liquid, and then we got our actual enthalpies for the products by using that basic equation. Enthalpy is equal to the enthalpy of formation plus the enthalpy at the product temperature minus the enthalpy at 77, our reference temperature. Basic equation that we're going to use. All right, last thing we wanted to do is try to make some sense of that number. Are our calculations reasonable, and how do they compare to standard numbers? So what we want to do is find the higher heating value for ethane and the lower heating value for ethane and compare our final number there to those values. So go ahead and go to the tables. Those are near the end of the tables, and get those two values, and we'll come back and compare in just a second. Okay, so I'm writing down HHV and LHV, and I'm flipping to the tables at the end. Okay. A27E has ethane in there. A27E has ethane. By the way, I should have said at the beginning we're just doing ethane gas. All right, ethane gas. So let me give me a second just to read those carefully. All right, here we go. Quick check to make sure I'm on the right line. There we go. All right. So hey, let's say you're out there in industry and you're doing some planning where you're going to burn some ethane gas, and you're wondering how much energy you've got get out of it. Well, the first thing to do is to take a look at the higher heating value and the lower heating value. So I got those higher heating value from the table. 22,320. Okay, what does that mean? That means if you burn ethane and the products come out at 77, and if the water comes out as liquid, you're going to get 22,320. All right, we're not even close. Why aren't we getting that value out of there? Well, first of all, the products are coming out at an elevated temperature, and also the products were vapor. Okay, what about the lower heating value? That's saying, hey, you probably are going to get about 20,000. You're probably going to get about 20,000 out of ethane. But once again, that's if the products come out at a lower temperature, and instead we're coming out at 1,200 Rankine, so we're getting much less out of it. So if you're doing some planning for machinery or some sort of heating process where you're going to burn some fuel, be careful about using the higher heating value or lower heating value. You really may need to go through and do this sort of analysis where you have some way of determining what the outlet temperature of the products are, and then you can go through and actually figure out the actual heat that's going to be released. All right, that's it. That's the last lecture on this stuff. So let me just talk for a little bit about finishing off the class. We're going to have a test 3 next week. Bottom line is that you want to do a good job on homework 8 and homework 9. I have homework 8 from a lot of you guys, and I've entered it in my gradebook. You can come by next week and pick it up from me. If you haven't done so already, put in that time on homework number 8. And then homework number 9 is 4 problems. Set aside a little bit of time. 2 diesel cycle problems and 2 combustion reaction problems where we have temperatures other than 77 degrees Fahrenheit or 25 degrees C. All right. Test 3. I know there's a lot of questions about when it's going to be. I hope you can trust that I'm just doing the best I can to find something that will work for everyone. Regardless, it is not going to be Monday morning at 8. Test 3 will not be Monday morning at 8, and I'll be communicating with you guys, and we will do it we will not do it Tuesday either, sometime later in the week. So wait for an update for me on that. Also, I'll be sending out an email with some times I'm available in RVR 1005 if you guys want to come by for extra help. All right. So that does it. I hope you got something out of this. Regardless, try those problems. 15.4 is another good resource, and we will talk next week. Take care.